Thanks for joining. I am Yashpal. Along with me, my colleague Akif, and we will be sharing our journey of using local storage volumes on K8s and hosting, large-scale distributed systems, right? And we are part of a central platform team at Flipkart. So let's jump right into it. This is what we're going to cover today. We'll set up some context on a bit on Flipkart infrastructure, and we'll set the objective, why we chose to use stateful or chose to host stateful workloads on Kubernetes. We'll share our findings between local and network attached storage, what's the differences you should take care of, and then we'll share our journey with respect to challenges and the solutions that we have done. Few of the product experience and the success stories of using local storage from last couple of years, and we'll leave the session with few key takeaways. Okay. Just a bit introduction about Flipkart. Flipkart being one of the largest e-commerce company, like many of you might have shopped from it, and from the Flipkart infrastructure point of view, we have like 6,000 microservices, all being managed by like 1,500 developers. The infrastructure comprises of 3 primary regions with presence in 2 on-prem and 1 public cloud. And we have total storage footprint of around 350 petabytes, which is like a local storage. And all of these are actually serving 2.5 million QPS from our public endpoints during the flagship event last year, the Big Billion Days. Just taking a bit of detour. So basically, before we dive into how the local storage is being leveraged, let's first look into the stakeholders involved in the overall infrastructure. So you have a central platform which provides cloud-like interface to various developers in Flipkart, and then we have IS service called infrastructure team, which takes the physical server and provide you the bare metal and virtual machines. And on top of that, we have Kubernetes platform team, which sort of provides a platform or manage K8s clusters at scale to host containerized applications. And on top of that, we have a database platforms which provides managed databases to various teams in Flipkart. So we have 2 groups of application teams, one who directly uses this managed databases, and one who directly manages their databases lifecycle using the infrastructure services, as we see here. Just to give a historical background, so Flipkart has been using VM Stack before 2021, and all the application teams used to manage the lifecycle of applications by themselves, right? Let's set up a context on why we started looking into hosting stateful workloads on Kubernetes. Before coming to stateful, we have already experienced a lot of benefits from stateless workloads on Kubernetes, as listed over here. As we all know, K8s provides the unified APIs and tooling to interact with the infrastructure. So it makes the overall cloud, cloud ready. And apart from that, K8s being providing the framework to host the applications, it substantially improve the operational efficiency of the overall organization. One of the unique things that we have done as part of onboarding K8s is that we started hosting the containerized application directly on bare metal. That means we remove the overhead of virtualization, and we effectively started using the physical hardware and improve the overall application performance along the way. And as we see, right, we have many other benefits of K8s, and we want to leverage those benefits for stateful workloads. That's the thought process we started with. Along with that, we have a bunch of unique things for stateful workloads that K8s provides. One is this operator pattern that we are all aware of mostly where it provides you a framework to automate or to develop the automations for doing the day-to operations for databases. Like you want to take a backup, you want to take upgrades, failure recovery. All of this information could be encoded within the operator itself. So that framework itself helps in reducing the operational cost of maintaining this database platform. Along with that, it sort of provides you a CSI interface, which essentially provides a consistent APIs to plug and play with different storage providers. So we want to experiment and improve our velocity of doing the experiments with different storage providers, right? So at this point, the organization has established that there are some of the benefits we want to leverage for hosting the databases on K8s. So we started looking into various sort of storage types that we want to use. So we have like local storage and network attached storage. Like local storage, where you sort of have the storage devices directly attached to the compute instances via various buses like PCIe or SAS. And then you have something like a network attached storage, where the storage devices are disaggregated from the compute, and you access the storage devices over the regular network infrastructure. Here are the few benefits between local and network attached storage. You can see local being directly attached to the compute instances provides the best performance, and it provides the best cost of hosting the storage devices. But it comes up with the cost of having the operational activities required to maintain such a large fleet of local storage. And like we understand, the storage devices are tightly coupled to a specific nodes. That means if the node becomes unavailable, your data will be lost, and you have to somehow recover the data from some other replicas. Whereas in case of network attached storage, those things are being taken care because you have effectively disaggregated the compute and the storage devices. And you can move around the workloads from one compute device to another compute device, attaching the same storage device. Okay. So we started looking into different sort of use cases in Flipkart, which are best suited for local storage. Given pre-2021, a lot of our infrastructure is already equipped with local storage. So a bunch of distributed databases where the replication is already being taken care by the application layer were best suited for local storage, because even if few of the nodes goes down, you still can recover the data from the other replicas. Again, there are a bunch of critical user-facing applications developed in Flipkart, which requires unprecedented performance, from the storage infrastructure. So we want to leverage local storage for that as well. We don't want to invest on the network attached storage infrastructure to begin with. So the overall cost we are looking at was to use the local storage itself for the existing applications. We have already realized there's an operational complexity in managing the local storage with VM stack experience, and we sort of have accepted a challenge in enabling local storage on Kubernetes, given the framework that Kubernetes provides to automate things. Here is a quick snippet of the cost and performance comparison between local storage and network attached storage. From one of the public cloud called Google, right? And as you can see, local storage sort of provides you 2x to 4x better IOPS and throughput with half the cost, right? So it's something worth evaluating, is what we have recognized overall in Kubernetes. So now I'll hand over to my colleague, Akif, who will walk us through different challenges and sort of solution that we have developed to enable local storage and use it effectively on Kubernetes. Over to you.
Thanks, Yashpal. Hi, everyone. So now that we understand why we wanted to onboard our workloads onto the local storage, let's take a step back and see how stateful is managed in a Kubernetes environment. So as a cluster administrator, they can create a storage class, and storage class is something which exposes the underlying storage infrastructure that a user may consume in the K8s infrastructure. And then the user can create the persistent volume claim, which can bind to a certain storage class that they want to consume, right? And in the pod spec, when they specify it, the underlying CSI provisioner takes over and actually provisions the volume on the storage infrastructure, right? Once that happens, the persistent volume object is created, which is bounded to the PVC, and the PV is now available for the consumption by the application pod, right? Few other points to note about our infrastructure is we have a multi-tenant K8s environment, meaning we are hosting workloads belonging to different business teams into a single cluster, right? So we manage them by scoping those workloads to the namespace, and they are tied to a certain quota, be it related to disk or CPU and other resources. So this is how local volume landscape looks like on a certain node. So if you see over here, let's say if you have a couple of pods running on each of one of those nodes, the SSD that is attached locally to the node has a couple of local volumes hosted on them. Right? So this is what the local storage is essentially. Now, while we were going towards the journey of bringing in the local PV infrastructure and looking at transitioning our tenants from VM to K8s world, there were certain set of challenges that we were supposed to solve, or that we were meant to solve when we wanted to onboard them. We'll go through each one of them one by one. To start with, we'll talk about dynamic provisioning of volumes. What do we mean by dynamic provisioning is that I would like to provision a volume on demand rather than keeping the volume provisioned beforehand when the node is provisioned. Right? So how do we achieve it, right? That is what we'll see next. So natively, provisioning in itself can be achieved by a couple of native ways that K8s provides, host path being one of them, right? Wherein what you do is you just take the certain path on the host node's file system and mount it directly into the pod. This is like not recommended for production grade workloads. It tightly couples the pod to the specific node, and it also has a potential security risk wherein you are exposing the host node's file system to the pod application. Right? So then we started looking at something else, right? So there is another way of doing it, which is with local volume. So though it solves or it decouples the pod tied to a node, right? It can like schedule the pod on any of the available node which has a local disk available, but it still had the other two problems intact. That is, it is still statically provisioned and it's not scalable for multi-tenant environments. So while looking at on how to solve this problem, right? We started looking around into the community and we started engaging with OpenEBS team, right? Which is a Kubernetes native storage solution, CSI compliant, and offers you local storage in K8s infrastructure. So in this context, while we were trying to solve the dynamic provisioning problem, OpenEBS supports it for a ZFS file system. But in our case, we were looking to also solve it for the LVM file system. Right? So given that it didn't have that support natively, we took it up and contributed it ourselves. Right? So just to, this is a bit low level detail around how the dynamic workflow goes like. So before we jump into it, I'll just touch upon the CSI controller that we see over here is a controller which is running at a cluster level, managing the OpenEBS workloads lifecycle. And then you have daemon set pods called as CSI node plugin agents, which are running on all of these stateful nodes, which are offering these local PVs. Right? So how a dynamic provisioning will work is the controller will keep a watch on the PVC. PVC is something that a user creates when they want to provision a volume, and the controller then in turn will create a LVM volume object. So LVM volume object is a custom resource that we have introduced, which primarily manages or it manages or it shares the details about the volume that is hosted on a certain node, right? So once that volume object, LVM volume object is created, the node CSI node plugin running on that node will reconcile that object, and it will create the actual LVM volume on the underlying storage, which is attached to that particular node, and it will update the status of this object. So, which in turn is consumed by the controller, and once this has been successfully created, the controller then will create the PV object, which is ready to be consumed by the application. Right? So, if you see over here, we were able to like dynamically and on demand were able to create the LVM volume onto the node when the user requested it by creating a PVC. So, this is how we solve the dynamic provisioning problem for LVM volumes. Next, moving on, the second problem that we had was around the scheduling. So, with local attached storage, the primary question that should has to be taken care of with respect to scheduling. I mean, the previous talk was primarily around it, I believe, right? So, you also have to make your scheduler aware of the disk capacity available on the node. Primarily, the scheduler only accounts for the CPU and memory, and basis that it takes the decision where to schedule the pod. So, in our case, so this is what the problem is, right? So, the scheduler is trying to put a certain pod which has a disk requirement of 512 GB, right? With a most allocated strategy and only accounting for CPU and memory, stateful node 1 looks like a right fit, but given that it is not aware of the disk requirement of the pod, the scheduling fails, right? So, the question remains that how do you make the scheduler aware of this disk requirement, right, of the pod, and also expose what is the disk available on the node, right? So, to our rescue came CSI storage capacity, which is a K8s native resource, stable since 1.24 K8s version, which essentially allows you to track the capacity available in a certain node topology. So, in our case, we chose that topology to be an individual node, right? And the scheduler then consumes this particular object while taking a decision of scheduling a certain pod. Right? Now, given that natively you have a solution available, the next question is how do you implement it in your existing infrastructure, right, and make it work in an automated manner. Right? So, again going back to what we saw earlier with dynamic provisioning, you again leverage the reconciliation and the management of the CSI storage capacity object to the CSI controller, right? And the controller will in turn read the LVM node object which is associated with the node, right? So, let me talk a bit about LVM node. Right? LVM node again is a custom resource that we ourselves created. The job of this object is to have the available capacity or track the available capacity on that node at any given point of time. The life cycle of this is managed by the CSI node plugin agent running locally on that node periodically, right? So, it has the latest information about what free capacity is available across the volume groups hosted on that node, right? So, the controller leverages this object, reads that available capacity and updates the CSI storage capacity object, right? So, the problem that we had in first place, that how do I cascade the nodes free capacity available to the scheduler, this is how you can do it, or this is how we did it, right? Now, with all that information available, scheduler now can happily consume the CSI storage capacity object, and now given that it's aware of the disk capacity available on each one of these nodes, it's able to successfully put the pod onto the stateful node. Right? Moving on, so with a multi-tenant environment, right, noisy neighbor is a very infamous problem to solve. What does it mean in a very layman language is that, let's say if you have workloads belonging to two different tenants hosted on a single node, they can like eat up resources for each other if not limited, right? Or if they are not restricted. Right? So, what we see on the screen is an example of a local SSD storage which is there on a node which can do 50K max IOPS, and it has a size of 1 TB. Right? Now, you have two workloads called as workload 1 and workload 2. Each one of them have 700 GB and 300 GB of size. Ideally, let's say if you go proportionately, I would have wanted workload 1 to do 35K IOPS, that is 70%, and workload 2 to do 15K IOPS, right? However, workload 1, let's say if it goes rogue, it can do much more if not restricted, right? So, as we see over here, it is doing 40K IOPS, upwards of 40K IOPS, and it's eating up resources that workload 2 was looking for, right? So, the question over here is how do I apply these expected IOP limits to these workloads, right? So we, in our infrastructure, we have Debian images on top of which all our worker nodes are hosted, right? And so in the Linux kernel space, there is something called as C group. So C group is a very popular feature which allows you to manage the resources at a infrastructure level or at a kernel, in a kernel space, right? So we leveraged it and to set the IO limits for the pods, right? So you can set it at different layers. We chose it to do it at a pod layer, wherein we say that, okay, for workload 1, you do 35K of IOPS, and for workload 2, you do 15K of IOPS. Now, given that you have an underlying feature available, how do you implement or how do you integrate it in your implementation, right? So again, on the node, the CSI node plugin agent that is running, right? It has an optional parameter of set IO limits, using which, or you can leverage it to configure and set these IO limits whenever a particular pod is supposed to publish a volume on a certain node, right? Essentially, when a volume is supposed to get mounted for that particular pod, right? So that is when you set these limits, and the workload then will operate within those limits, correct? So this is how we have solved the noisy neighbor problem, wherein workload 1 cannot eat up the resources that are specifically provisioned for workload 2. Yeah, so these were primarily the highlighted problems that we solved. There are a couple of other features as well that we have solved, which are listed over here. The link that I've shared is a OpenEBS link, wherein all our contributions that I've spoken about are available. Please feel free to take a look. Next, we would like to talk about the day-to operations like maintenances and our success stories that Yashpal will cover. Thank you.
Thanks, Akif. So let's look at how we can do the infrastructure level maintenances for these workloads leveraging the local storage, right? Because given the pods and the volumes are tied to a given node, whenever we do any sort of OS version upgrades or Kubernetes version upgrades, the workload will get disrupted, right? So how do we make sure that the disruption is minimized and make it operationally easy to do both at infrastructure layer as well as the database platforms, right? So first thing is that, like I mentioned, like during the upgrades, the underlying workloads will be disrupted. So let's take an example of how they may look like. So let's say we have a stateful workload or a database workload which is replicating the data among two volumes. Let's say both of these volumes are hosted on node 1 and node 2 respectively. And we want to do some maintenances on node 2, be it a K8s version upgrade or OS version upgrade or firmware upgrades, anything, right? So the usual way would be that we take the node down for some brief amount of time, and we do the upgrades, and we invert back that node again to the cluster, and so that the workloads can schedule back on that node again, and then you have all the replicas of the database volumes available to use. But with this approach, you are making the operation more reactive. Because during that brief period of time when we are taking the maintenances, there's a risk involved in losing the other copy as well. Because the unplanned maintenance can happen in a large infrastructure at any point in time. So instead of doing it reactively from the database platform side, we chose an approach to do it proactively because the schedule of the maintenance is available ahead of time. So instead of database platforms doing it during the maintenance, they started doing it before the maintenance even start. So in nutshell, the database platform needs to be aware of the schedule of the maintenance that the infrastructure team has planned. And that is where we have developed something called a maintenance workflow, where we sort of publish those maintenance events in form of custom resources within the cluster. And then the maintenance controller will translate those node level maintenances to individual volume level maintenances hosted on that node, because we want to notify individual tenants hosted on that node. So after those volume level maintenance custom resource being available, those can then be consumed by the database operator. The automation can be created by individual database platform teams, to proactively move or like create an extra copy of their volume replicas to some other node so that they can avoid, under replication of their data, right? Okay, so till now, I think we have talked about a lot of solutioning. So we sort of have been on this journey from last 2 to 3 years, and we have onboarded, 3 critical database platforms, which are being operated at a very large scale at Flipkart. So these are like Aerospikes, HBase, and TiDB. All of these are hosted on, 1,000 plus local storage enabled K8s nodes, and which accounts a total of 19 petabytes of storage. Given, like I mentioned in the previous slides, we are operating Kubernetes on bare metal, so we sort of also witnessed a substantial improvements in performance by eliminating the virtualization overhead that comes with the virtual machines. Apart from that, as we transition from the VM stack to the K8s stack with day 2 operations automated, we sort of identified that the teams are moving a lot faster, and like the operation efficiency came out to be 3x. Okay. Right. So at this point, we also sort of started hosting the very similar solutions on the public cloud, because again, the cost of the public cloud can easily spike up as you start scaling up your workloads. So we adopted the same LocalPV solutions that we have, implemented internally on-prem to public cloud, and in our case, we are using GCP. So specifically on GKE, we sort of created a dedicated node pool hosting these local storage workloads, and we have disabled the auto upgrades that GKE usually do. The reason being that we want to orchestrate the maintenance of these nodes, by ourselves and stitch together with the maintenance workflow that we have implemented on-prem. Apart from that, there are some cost savings we have observed with hosting this DB platforms, especially around Aerospikes. We have seen around 8x cost reduction because of the nature of the workload itself, where it requires a high IOPS, right? And for the other database platform, the cost reduction came out to be 2x. Right? So having said all of this, local storage is not for everyone. So having a clear understanding of what are the caveats, where it works, where it does not, we have added something called identified some of the limitations in operating it. So we have talked about CSI storage capacity tracking in the earlier side. So there's a limitation where you cannot, host workload mounting multiple volumes, multiple PVCs with CSI storage capacity today, because of the way itself the feature is implemented. Along with that, given the workload is tied to a specific node, there is a limited scope available to support the vertical scaling of this workload. So we have enabled some policies in the cluster where we have disabled the vertical scaling, be it in terms of compute or storage, for the workloads hosted on those nodes. Here are a few of the work that we are doing internally at platform side. We want to have more DB operators to leverage our maintenance, workflow, so that the day 2 operations are, optimized. And we want to have the whole fleet managed by a cluster API. So we are internally working on automating the management of the K8s cluster itself, and the maintenance lifecycle of the LocalPV nodes as well. We want to stitch it together with the cluster API. Along with that, we are exploring, can we enable the snapshot support if you want to take data backups from the infrastructure layer. So here are the few key takeaways. Like I mentioned, we sort of only adopted the workloads which are distributed in nature and consistently replicated across multiple nodes. So embrace the application level replication itself in your infrastructure wherever is possible. Again, do a deep analysis of how the performance and cost comes out for the storage solutions that you are choosing up with. One of the key success that we have seen with LocalPV is with automation. So it's not an optional thing. If you really want a success, automation should be done because it might pile up with respect to operationally hectic exercise as you scale up the infrastructure or the developer community. So we started leveraging the cloud-native ecosystem itself. Rather than building something in-house, we worked with the community, developed these features together with the OpenEBS, and it came out to be a win-win situation, both for the Flipkart as an organization as well as the community where they can leverage such solution. Again, like I mentioned, understand the trade-offs between local storage and the network-attached storage. So Kubernetes as a orchestrated system natively supports network-attached storage quite well. In simpler cases, after doing all this evaluation, you may want to choose network-attached storage based on the trade-offs you are looking for. So that's all from us. Let us know if there are any further questions. Happy to answer them. Thank you.
Hey, hi. Yeah, thanks for the talk. So I just want to understand how does, like, if a node goes down, for example, with everything that is considering having workloads. So I understand that only one workload will have one storage volume, right? Because of the CSI thing. So if that particular node goes down, what is your normal strategy to like replace it? So do you have MySQL backups and you will like restore it, or just restore the entire node normally?
Okay, so the question is, if the node goes down, how do we recover the data which was hosted on that node? So usually, this is done by the database itself. So we usually don't prefer to host single master systems like MySQL on this kind of storage solution, because if we don't want to risk the data being lost if one of the node goes down. Some of the distributed consistent replicated databases that we talked about, right? HBase, Aerospikes, or TiDB. Even if a few of the nodes goes down, you can still recover the data from the other replicas hosted on other nodes. So, and that is being automatically done by this distributed database out of the box. So you don't have to build the solution for doing that.
Hi, Suraj here, in the first row. Okay. I actually have two different questions. First one goes to, how do you manage the volume expansions? Like, the disk is limited. Let us say you have allocated 300 GB of it, but the resource he's actually eaten up each and everything, and he's now running out of the storage. So how do you resolve it?
That's a good question. So in case of local storage, that is not possible, to be honest. So what we usually recommend to the database platforms is that create a new cluster, replicate the data if you want to vertically size up, and then decommission the older cluster. Because like you mentioned, there is a limited resources. So we deliberately disabled the expansion for the workloads hosted on this local infrastructure.
Okay, get it. Other question. So in terms of scheduling, so you have written something which will get to know about the existing space on that particular node. Have you guys tried writing your own scheduler which will actually do the same thing for you?
Again, a good question and something that we have explored. See, there is a maintenance cost whenever we introduce more components. So we sort of started looking into a native way of doing that. And fortunately, at the time when we started this journey, there was a feature was available called CSI storage capacity, natively supported in Kubernetes. I think we were a few of the first few folks who has leveraged this storage or these features where we populate the available capacity on individual nodes into these objects, which the Kubernetes control plane further leverages it to schedule the pods onto the right node.
Yeah, the solution that you are trying, that's like another solution, which is obviously going to work for you. Yeah. But yeah, on the scheduler side, if you want to, you can even write your own scheduler, which will actually have, even better capacity executions. And as far as I know, I have even worked on sort of the same things. By the way, this is something when I was just playing around Kubernetes basic functionality. So you can even write the custom scheduler. It do supported totally native, totally extensive with cloud Kubernetes own plugins, and that will also help.
Sure, happy to chat about it. But I think our thought process at that time is just to leverage the native scheduler itself rather than building something by ourselves.
I get it. Cool. Yeah. Thank you. Thank you so much.
Yeah, hi. So you spoke about DAS and NAS storage. So why aren't you like considering using SAN? And in your case, if you are using DAS, then how are you basically doing the disaster recovery? Like if your primary fails, and if you are using NAS, that actually brings in the network bottleneck, and that has got performance repercussions. So if you are doing LVM and all other stuff, then why aren't you using SAN instead of DAS and NAS?
Yeah, so when we talk about network attached storage here, it's not just about NAS specifically. So it's more of about a storage which is exposed over the network. Whether in terms of, it could be done by a SAN or it could be done by a NAS. I think the thought process was that we had a lot of local storage in our on-prem data center available. We want to leverage that infrastructure rather than invest further on the a new solution called SAN. That is like one thought process at that time. And we also wanted to serve best value proposition with respect to the kind of databases we are trying to onboard, the kind of performance and the cost implications for those storage infrastructure. So on evaluating all these pivots, we sort of taking an approach of using local storage itself.
What about the disaster recovery part?
Okay, so the disaster recovery, that is again a good question. So basically, all these database platforms does the disaster recovery out of the band rather than using the infrastructure services itself. So if you see TiDB or Aerospikes, they have their own backup solutions where you sort of spawn up those backup tools and you take the data dump and you upload it to the remote offsite. So all of this orchestration is being done by the database platform encoded into the database operator itself.
Hi, this is Venu. Great talk, guys. Quick question. So you mentioned this, I think, a bit in your section about reducing noisy neighbors, but are you able to run heterogeneous SKUs in your Kubernetes cluster, or is it mostly homogeneous for that particular workload itself?
That's a good question. So we host multiple different type of storage classes. Be it in terms of SSD, HDDs, and we impose the QoS limits specific to IOPS and throughputs at a storage class level. When we define the storage class is pertaining to a specific homogeneous set of infrastructure.
Got it. Thank you.
Yeah.
With respect to capacity, so that it is running periodically, right? So I can say that scheduler is not getting updated about the capacity of the node in the real time. So let's say I have given acceleration policy saying 70–80%, and now that service is running after like 2 minutes or 3 minutes. So what will happen for these 2 to 3 minutes when scheduler is not updated?
That's a really good question again. So Like we mentioned, the capacity tracking feature that we have enabled actually just tracks the capacity asynchronously. That means if there's a burst of workload which wants to leverage the local storage capacity, how do we enable the consistent information coming from the node to the scheduler, right? That is not possible, but there's a workaround to do that. So when, let's say, the scheduler schedules a given pod to a node where there's no sufficient capacity, the node agent sort of responds back saying that the volume creation has failed, and the controller plugin again responds back to the external provisioner here, saying that the resource exhausted. So basically, this is a unique code that we sort of expose from our CSI plugin to the controller plugin, which is being used by the scheduler to reschedule the pod after the capacity information gets updated eventually on the control plane.
So I believe there's like a small downtime into it. Like if the pod goes to the node and then it says the resource is not here available, and then comes back, and then again the quota is getting updated or something like that.
Not downtime. This happens only during the volume provisioning workflow. Okay. So if during the volume provisioning, if there is no sufficient space available on the node, we sort of use this fallback mechanism where we respond back to the control plane in certain codes, which enables the scheduler to reschedule the pod onto some other node.
Thank you.
Hello? Can I go? Yeah. I think you are using the C group feature to set the IOPS limit. One question, so how do you derive those limits, and how these are set dynamically or statically for each worker node?
It's dynamic in nature. So what we do is in the plugin itself, there is an optional feature that you can pass called as set IO limits. And we can configure the plugin saying that, okay, I want to set, let's say 50 IOPS per GB size. So we have done it size based, right? And whenever a workload is supposed to schedule on that, the CSI plugin will read that value, and basis the size of the volume, it will calculate that value and will set it. So
thanks.
Hold a second. Hey, one question. Can you just help us out? Like, how did you achieve multi-region replication using that?
For the databases?
For the databases, yeah, for the data.
I think we have one more feature internally. We call it multi-cluster service discovery. So basically, this databases internally are replicated. All the configurations about hosting the databases across the multiple regions are being done as part of setting up the database itself with the right endpoints where you want to do the replication. Now, in order to expose the endpoint information from one cluster to another cluster, we have this feature called multi-cluster discovery. Maybe we can do a talk sometime later about it. Yeah.
The data sync is async or asynchronous?
It really depends on the use case. So different tenants may want to have a trade-off between performance versus data reliability. So as an infrastructure team, we don't have that visibility, but yeah, I mean, it could go in either ways.
Thank you.
Yeah.
Hey, hi. Over here. I have a question related to the dynamic provisioning, right? Like, so when the dynamic provisioning is happening, I assume it's with the live database, right? So when the dynamic provision is happening, did you guys face any data corruptions after the new PVC gets provisioned and attached to the pod?
No, not really, because you use this battle-tested volume manager called LVM, which sort of segregates or create a logical volumes for individual workloads that we are hosted on it. And yeah, I mean, that's pretty much it. Like we had a lot of experience in LVM in VM stack itself. We leveraged that experience, in enabling the similar solution on Kubernetes.
Thank you. Transaction. If the database is transactional or RDBMS stuff, right? Like, do we have any kind of corruptions happening at the database end? Like, because it will be like consuming the volume sequentially, right? Like, without any gaps. So I understand the new provision volumes gets attached to the PVC, but was there any situation like any kind of data corruptions observed in the logs, database logs?
Not really, like because each of this volume that we provision is tied to a given workload pod. It is not, it cannot tie to any other workload pod. So those sort of constraints are enabled on the volume to make sure this kind of situation does not arise.
Thank you.
Hi, I have a question about isolation. So you mentioned about IOPS. How do you enforce isolation for the storage itself so that one pod does not eat into the storage of another pod?
You meant to say
Size.
the size of the volume,
Yeah, so you have a PVC that's attached to one pod, and there's another PVC for another pod. How does the first pod how is the first pod prevented from eating the storage of the other pod?
So each of the workload volumes are created with a fixed size volumes, right? And we have this CSI storage capacity feature being leveraged, as I talked about. As part of the scheduling of this volume to a specific node, those are being taken care by the control plane itself.
Okay, that would manage the size itself, I guess. So maybe 100 gigabytes for pod 1 and 200 for pod 2. But is it possible for pod 1 to go above 100 gigabytes?
No.
Okay.
So that is being restricted with volume manager itself. So we use the LVM itself. The volume manager makes sure that it does not have, or the application does not go beyond the size of the volume.
Okay, got it. Thank you.
So this is a follow-up question which the last person that asked. So when a PV get provisioned on the node, local storage, that is a thin provision or thick provision? Like the whole capacity will get allocated at the time of provisioning, or like it will be a dynamic increase, it will get dynamically increased and will stop at the limit that we set there?
That's a good question. So we have explored that given the nature of the infrastructure, right? So we have a fixed size disk available on the compute, right? At the end of the day. So we sort of have not used the thin provisioning yet. Maybe something we want to explore further if we see a burstability in terms of the usage of the storage, right? So that is something we can explore, but it needs to be used with some precautions, right? Because
the issue that would arrive that will be regarding to the under provisioning or over provisioning of the storage. If those two things will not, we will not consider those two things while provisioning of PVs. So that's the issue that came in my mind.
Right. So that is one of the reasons we don't use that right now, the thin provisioning. But it's something worth to look at if depending on the workloads you are hosted on.
Because we are leveraging the feature of local storage. That's why I asked this question. Because I'm from the VMware background, so I know like you are having your local servers there, and you are provisioning your local storage there and attaching whatever the infrastructure you were having back then. You are using the same infrastructure to provision Kubernetes clusters.
Correct.
Yeah,
that's correct.
Thank you.
I had one question related to the C group settings that you talked about, right? So you are limiting the IOPS on the pods using the C groups and isolating there. But like, how do you make changes to it? Like if I have provisioned it and then I have to update it, then like how does that workflow look like?
Right. I think we have a slide for that. So basically, as part of the volume, mounting the volume to the pod itself, there's a workflow involved between kubelet to the CSI node provisioner. And as part of that implementation of that workflow, we have taken a call to impose the IOPS and throughput limit at a pod C group level based on the size of the volume that we are trying to mount.
Got it, thanks.
Okay. Hey, one more question here.
Okay. Okay, I think we should end this session now. So thanks everyone again. Happy to chat further.
Yeah, thank you.
Thank you.